So first of all, let me thank you, Kirsten, for the opportunity to speak today. I want also to thank Fernando Naredo and the whole European Nuclear Society for the opportunity to talk about this nice topic. I hope that given the context and the challenging times, everyone listening today is safe and can take care of his loved ones. And I hope that to this hour will be a bit more fun in these challenging times. So without further ado, I propose that we get into the presentation right away. Why is my eye? All right. So today and over the next 30 minutes, I will talk about small modular reactors, and I will try to answer one essential question, which is, can SMRs enable an affordable zero carbon transition for the European power grid? But before we dive into the economic study we performed, and I want to share something that I truly got to believe over those last 2 years while I was working on the topic of SMR. And that is that I'm more and more convinced that small modular reactors may very well be the next big thing for the nuclear industry and even for the energy market as a whole. Okay. You may wonder why I formulate such a strong statement. I would say that the reason why Tractebel does believe in SMRs and why we think small modular reactors are different is because it is a business model that starts from the right questions. And they do bring pretty sensible answers to those questions. So usually when I'm talking about this topic, I try to summarize those questions into 4 main questions. The first one would be, in the post-Fukushima context, how do we recreate trust in nuclear safety? This is not an easy question to answer. For sure, there is a large variety of SMRs that include different technology, very different technology. But I would say the common threads within the SMR business model is the following. They aim at making safety simpler, which means simpler to explain and simpler to understand. What I mean by that is that to a large extent, small modular reactors rely on passive safety systems as well as inherent safety characteristics rather than engineered safety features. That means that rather than designing complex solutions, you try to rely on physical phenomena that will bring you to the same level of safety. And this choice has 2 major benefits, or at least 2 major benefits are sought with this approach. The first one is to make sure that even in the worst imaginable events, the operator has an extended period of time in which that would be of about a couple of days, during which the reactor will remain safe even without any operator intervention, and that gives them the time to be able to react to any situation and to have the time to handle those situations. The second benefit of this passive and inherent safety approach is to try and reduce the radiological consequences even in the worst case scenario. That means that radiological consequences with adequate design choices can be reduced to a level such that the impact of any accidental condition is limited so that you don't have to evacuate people outside of the site boundary. So that, I think, is really the driving factor behind the approach towards safety of small modular reactors, and I would say that it is the first big step of why SMR brings something new to the nuclear industry as a whole. The second question would be, in a context where we've seen that nuclear new builds have known quite challenging construction issues and certainly large financial burdens with multi-billion dollar projects, how can we boost financial appetite for nuclear projects again? And I mean, this is a very difficult question that a lot of countries have tried to answer in different ways. With regard to SMRs, the main idea, the main approach behind the SMR business model is to try to aim at standardization of the modules, as well as making projects smaller. The idea behind that is to have more control over construction issues, a better a construction process that is better mastered, as well as reducing the financial risk that investor would take with a nuclear endeavor. And typically, to give you an order of magnitude, I would say that the investment into a large nuclear reactors would be in the size of 10 billions, the order of magnitude of 10 billions of dollars. SMR targets an order of magnitude lower than that, and that brings very innovative possibilities for SMRs, because it means that even actors that have less financial power than the traditional giant that can afford a nuclear reactor or the state can also join or can also build small modular reactors. So I would say that the second changing point. The third one, I won't spend too much time on today, but I would like to mention still the fact that some solution brought by some fast spectrum small modular reactors or advanced modular reactors are able to reduce the radiotoxicity and the volume of nuclear waste. And we know that for sure. I mean, anyone that has been working in nuclear energy right now probably has had a discussion with his families or friends about what is the impact of nuclear waste. Of course, there are technical solutions, valid technical solutions that have been put forward, but having the ability to reduce the radiotoxicity and to reduce the volume of nuclear waste, especially spent nuclear fuel, is definitely an advantage. And then I would say the fourth question, and the one we will spend more time trying to understand today, is how SMR can play a role into the zero carbon transition. I will already give you very quick elements into what that entails. First of all, we know the context of having a lot of intermittent renewables having a growing share of the production mix. That has its challenges. We know also the context of climate change that asks for a rapid decarbonization. SMR try to tackle both those elements. I would say for the first one, we know that nuclear energy is a decarbonized energy sources, but SMR brings something new, which is flexibility. Flexibility understood as the flexibility to balance the intermittency of renewables. That's a cornerstone of the SMR business model. And then I would say the second element that I won't be covering today is that some of the SMRs try to tackle sector of heat production for process heat application, industrial application, that is harder to solve with only wind and solar energy. So really being able to drive a deep decarbonization process outside of the normal areas of nuclear, or at least of renewable energies. All right. Last thing that I want to say within this introductory part is that we see SMR as a growing market. I should say that SMR is not a single product. In fact, over the last few years, indeed, we've seen growing interest in the development of small and advanced modular nuclear reactors, with more than 50 companies being both established companies, but also startups, developing their own products, and that's in more than 10 different countries. So when I was saying it's not a single product, I really mean there is a variety of products, as I said, more than 50, but that cover also a lot of type of different reactors. There are more than 6 types of nuclear reactors on the SMR market. The light water reactors that we know and have today operating mostly in the world, but there are also some more advanced technology, high temperature gas cooled reactors, liquid metal reactors, all kind of technology that bring, I would say, very promising features for the future. And it is clear that the hype about the small reactors is real, but the question I want to focus on today is this hype backed by economic drivers? And so that's what we'll spend the next 20 minutes talking about. So this brings us to an economic study that we've performed within Tractebel, also with the help of our colleagues of ENGIE Impact that are kind of specialized in economic modeling, and that I'm going to present today. The idea and the goal behind that study was to understand to which extent small modular reactors would make economic sense for the European energy transition between 2030 up to 2050. With 3 objectives set. The first one, understand the economic driver behind SMRs. But we wanted to do that by going beyond the usual measurements that are used to compare energy sources, which is plant level cost comparison, usually done with the levelized cost of electricity, and really tackle grid level costs to try to understand some specificities that are brought by renewable energy systems. And one of those specificities is the need that the more you have renewable into your system, the more you need to have battery or storage capacities as well, and as a strong grid to be able to balance the intermittency of renewables. And so we wanted to see beyond levelized cost of electricity what that would represent and how SMR with their flexibility feature can help solve that. The last one, I won't have time to cover too much, but if you have questions about it, I can tell you a bit more, was to try and have or study trajectories across 2030 to 2050 to get a view of what makes sense over the transition period and how the share of SMR might grow into the future with the different technology that are existing today. So this brings me to the scope of the study, and let me start by explaining a bit about the methodology that we followed and how the market simulation study that we've performed works. I will try not to get lost in the details. I love that stuff, and sometimes I can really get into too many details, but I'll try to get to the basics. I would say that basically the market simulation study tool that we've used, that is called Plexos for those who might have heard of it, starts from today's energy mix and invests into new energy assets in each country, that are modeled to fulfill the demand of the European power grid. And this demand is also modeled based on some assumptions and studies that have been performed to try and measure also the growing demand of electricity in Europe across the 2030-2050 period. The tool that we use basically try to solve an optimization problem that aim at both minimizing the total system costs of the whole European copper plates, while also fulfilling some constraints on achieving carbon emission reduction targets that are in line with the ambition of the European Commission. And that means, basically said that if you look at the model, it's really trying over the different period of time, and you can see a graph on the left, on the right-hand side of the slide that shows that among the year, it will decrease investment into gas or carbon intensive technology. Also, to give you a bit of an idea of the granularity of the modeling that we've performed, you should know that we use a multi-year representation where basically we simulate 1 year every 5 years, starting in 2030 and up to 2050. And those runs simulate a full year with a time step of 1 hour. And that is, I mean, a lot of hours that are simulated across the year, but the idea behind that is really that we get the insight considering daily load variation, weekly variations, but also seasonal effects. We know, for instance, you see a small graph here where we know that the consumption of electricity is not the same in winter and summer. Solar power, irradiance, and wind blowing is not the same either. And so all of this is factored in based on statistical data and really this high granularity modeling. With regard to the scope of the study, we've also included multiple scenarios. So what is important to know is that we compare different scenarios to a base case scenario that came from an earlier study performed in Energy Impacts, where in this base case scenario, the idea was to go to the energy transition, to a zero carbon transition in 2050 with renewable energy systems only. And so in that case, investments are only allowed in renewables, gas and biomass, and for nuclear, the only thing that is allowed is lifetime extension that are already planned. So you don't have nuclear in that scenario. And we compared that scenario with other scenario where we gradually introduce investment into new nuclear assets according to their maturity. So in scenario 2, we allow investment into generation 3 reactors. In scenario 3, we allow investment into light water small modular reactors that should be, I would say, ready and commercially deployable by the end of the decade, and even maybe mid of the decade for some of the vendors. And then we've also allowed, in addition to those Gen 3 and light water reactors, investment into more disruptive technologies such as the molten salt reactors, assuming that they would be commercially available and deployable by 2035. I should also note that for this study, and because the goal is to reach, I would say, the carbon emission reduction targets, we did not allow investment into coal power plants, so the economic competitiveness with regard to that technology is not really tackled. So in terms, last thing I would say about the scope of the study is a word about the country scope. Basically, in our model, we've considered this European copper plate with, I would say, Western and a bit of Central and Northern Europe, but not the whole of Europe, the country that you see on the screen, in which we have allowed nuclear new builds into 3 types of country. One is the UK, which is an established nuclear country with a lot of potential for offshore wind. So we can see different challenges maybe from continental Europe. Then Switzerland, that is also an established nuclear country, well interconnected within Europe, and that also has a lot of potential for hydro energy. So that gave us a bit of an idea into a different profile. And the last one we modeled was Poland, a country that I would say whose energy production is highly carbon intensive, and that is considering nuclear energy in the near future with maybe a potential for renewables that may be a bit lower than in those two countries I mentioned before. Small disclaimer about the modeling of Poland. If you see maybe that in the data that there are something that are not fully aligned with written Poland data, it's because it's been modeled based on Germany data. Poland was not included in the first model, and so we wanted to try to include it as easily as we could, and so we used some of Germany's data as a surrogate and try to retrofit that concept. Then last thing I want to talk to you about that you can see on this slide is that the case study that we've performed accounts for several macroeconomic considerations. First of all, we account for the decreasing cost of renewable, and I should say that it's important to say that the assumption we've chosen for renewables are quite favorable. I wouldn't say they're too optimistic, but they are somewhat optimistic. Whereas the assumption we've used for nuclear are kind of our best estimate numbers. The idea behind that is that we didn't want to be too optimistic about the nuclear numbers and face some criticism. Second macroeconomic consideration worth mentioning, we've considered the electrical demand growth that also takes into account an electrification of energy consumption, for example, due to electric vehicles. Third point, the model considers also the cost of reinforcing cross-border grid connection. So each country that you see here is modeled as a point. So we don't have the granularity of, I would say, the inside grid of the country, but cross-border connection are indeed modeled and evaluated in terms of cost. And then last point is that we've also, of course, included the fact that there will be a need to invest into batteries and power to gas to power storage type to compensate the intermittency of renewables. And we've also used assumptions in the decreasing cost of batteries over time based on what we can see in the literature. So this now brings me to the results. First of all, small disclaimer, I want to say that the results that you see here are not a prediction of what we believe will be the future of the energy market in Europe. It's more a view of a macroeconomic optimum that would be achieved under some given assumptions that you've seen on the previous slides. Nevertheless, what our study told us is that there are great economic prospects for small modular reactors. I would say that where Gen 3 reactor at current cost estimation, that is about $7,500 per kilowatt electric, that was estimated based on the Hinkley Point C costs. Those Gen 3 reactors are barely competitive in the 2050 picture, except in countries like Poland. But even where we see that, we see also that for light water SMR, the share of production that is reached in the economical optimum in 2050 is about 25%, a quarter of the total production at least. That's the case in the UK. In Poland, you see that it goes even to 65%. And that shows that really from an economic standpoint, SMR do make sense into the energy mix. And of course, when you take very innovative reactors like the molten salt reactors that I should say target very competitive costs, basically due to two main aspects, size reduction and simplicity of their design. Well, of course, with those very competitive cost assumption, you get to a result that molten salt reactors fare even better than light water SMRs. But I would say that what is more important to notice about molten salt reactors is what we've seen in our sensitivity analysis, that even if you double the capex of molten salt reactors, because of course they are low maturity technology and costs may increase in the future, even though we've already accounted for a margin on the costs that are advertised by the vendors. Even if you double the capex, you see that there is still an investment into major installed capacity for molten salt reactors. And that is due to one of their features that I will spend a couple of minutes talking about in the last part of the presentation, which is their very high flexibility. So indeed, if you look at molten salt reactors, you see that they have very high load balancing capabilities. And this is due to one of the features of the molten salt reactors, which is the thermal or the heat storage feature of those reactors. The idea is the following. Instead of changing the power from the reactor side, molten salt reactors have an intermediate loop that comes from concentrated solar power with large heat tanks that are filled when they are not producing electricity and emptied when the turbine is producing electricity. And that allows to operate the reactor parts at constant power and removes any maneuverability limit on the nuclear reactors. So for instance, you can see an example here that comes from a UK company in where they foresee a storage capacity of 24 hours for a 1 gigawatt size reactor, and that can allow them, if they want to produce only for 8 hours 3 gigawatts. Of course, it means that they need to have 3 gigawatts of turbine installed, but the reactor nominal size is only 1 gigawatt. So it is quite a feature, and as we'll see in the next slides, it's something that that brings a lot of value to the energy market of tomorrow. I should say also that this feature of molten salt reactor is not new. For those of you who may know a bit about concentrated solar power, that should be familiar with that concept. This is a technology that has been built, and that directly comes from concentrated solar power, and where we see that storing energy under the form of heat is very efficient because you lose very low power across time, and that has, of course, benefits compared to what you could do with batteries. So what does our study tells? Well, if we look at the sensitivity analysis that we performed to try and optimize the storage and production size of molten salt reactors, we see that flexibility is clearly the key to complementarity with renewables. And this is specifically true in case where renewable may reach higher share of the production. You might remember from the first slide of results that I showed that from an economic standpoint, we see at first a very high penetration of molten salt reactors into the grid. This might not be realistic, and so if we limit that potential to 15%, as we did in our study, and as we can see on the slide, you see that the storage size, the optimal storage size, increases as long as the renewable penetration increases. And for a potential of molten salt reactors that is limited to 50% of the production share, we see that the optimal storage size is somewhere around 30 hours, whereas the turbine to reactor power ratio is about 1.6, 1.7, meaning that you would have for a 1 gigawatt reactor, a 1.7 gigawatt turbine to produce electricity. And I would say that this brings me to the most important conclusion of this study, which is levelized cost of electricity is not the whole story. In fact, if you look at the levelized cost of electricity in the scenario I just showed, you would see that the capex linked to this thermal storage and to increase turbine size makes it not so competitive with renewables if you look at first. This is also the case if you look at light water SMRs in the first case. But what we see is that if you can bring flexibility to the grid, the total system cost will decrease as the need for investment into storage option and interconnection option decreases. And that's what this conclusion slide shows here. So on the left-hand part of the slide, you can see the different scenarios, so starting from the RES renewable energy system only up to the scenario considering molten salt reactors, and you see that the total generation cost decreases when you include those light water SMRs. You should know that this is the total generation cost for the overall European power grid, and that the SMR option is only allowed in 3 countries. So we see that it leads still to a significant reduction of the total overall system cost, and this is because you decrease, as we can see on the right-hand part of the slide, you decrease the need for storage capacity in synthetic gas, so meaning power to gas to power, or in batteries. So this leads me to, I would say, the end of my presentation. And I would say that if you need to take away 5 elements from this presentation, those would be the following. First, for sure, small modular reactors are a promising market, even in Europe. And this remains true even if the vendors cannot achieve the advertised capital cost. The second point would be that SMR should be promoted together with renewable energy. It has been the case for long that proponents of renewables have tried to oppose nuclear energy and renewable energy. That's for sure not valid as a whole, but this is specifically not true for SMRs, for which you really see a synergetic mean of achieving a zero carbon target by 2050. The third point I would like you to take away is that levelized cost of electricity is not the whole story. And if you compare the levelized cost of electricity of renewables with other types, more base load or more flexible type of dispatchable type of energy, you see that you miss something very important, which is that renewable induced infrastructural costs, profile costs, storage costs, transmission and distribution costs that are not accounted into the LCOE picture, and the flexible nuclear option allows for a decrease of the total system cost. So even at higher LCOE, it is a good complement and brings down the cost of electricity as a whole. The fourth point is that for those new, I talked about molten salt reactors, but as a general comment, for advanced nuclear reactors that can have enhanced load balancing capabilities, such as this heat storage feature I just presented, we see that these load balancing capabilities can be a viable alternative to electricity storage. And this is true even if you need to reach high capex. So it should be said, because indeed in fact what it shows is that if you have flexible energy solution, nuclear energy solution, you in fact increase the value of renewable energy system into the grid. And the last point is maybe more focused on future developments. What I just presented today was focused on the electricity market. But the thing is that most of the small modular reactors are also looking at the decarbonization of non-electric energy markets, such as hydrogen production, district heating, petrochemical heat market for the, I would say maybe not in Europe, but for the Middle East and Southeast Asia, also at water desalination. And we are currently looking to extend the study we've performed into those new markets, because we really do believe that they can bring very valuable prospects. So that's all for the presentation. I want to thank you for listening to this.